Well, we've known now for some time that the sun goes through cycles of more explosions on the sun, more emissions from the sun. It was only in the 1950s that Gene Parker revealed that there is a solar wind. He was ridiculed at first. A wind from the sun, well, it's not really air blowing, it's particles, broken bits of atoms streaming toward us at a couple hundred miles a second, and you figure about 10 particles for every bit of space the size of a sugar cube on average, but easily gets to 100 or more depending upon how active the sun is. So a big explosion, a CME, a coronal mass ejection, we can get up to 10 billion tons of material from the sun slamming into us, and that's when we really have to watch out. Then we get our satellites knocked out of commission. We get radiation in polar regions. For example, jetliners flying polar routes, all the crew and the passengers get more radiation than they would really like to get, and their radio communications are knocked out, so they can't communicate, which isn't a good thing there. And GPS gets knocked out. And what happens next depends. The swarm has its own magnetic field. If this swarm's field is aligned the same way Earth's field is, well, then our magnetosphere channels all that stuff harmlessly past Earth and nothing happens. But if that swarm has a polarization that's opposite ours, that's a 50-50 shot, then it transfers its energy. And all of a sudden, along those magnetic field lines, you get charged particles, and this generates electricity. And I'm talking about big league electricity that makes lightning bolts seem like a little expired battery by comparison. This super electricity ionizes the air, mostly about 100 or 120 miles up. If it's oxygen, nitrogen will often get a green color at 5,000, just over 5,000 angstroms, or a red at 6,400 angstroms. But our eyes are very insensitive to red light, deep red light. So we see the green, and that's what makes an aurora, a green aurora, very, very common for us to see. So that's